first thing that we're going to do today is we are going to try to guess what the x-intercept of this curve is. Now that's going to be really difficult to do because quite obviously there's no scale here on our graph. And so who knows what these values are. So we're just going to kind of think about it arbitrarily. And we're going to start by making a really terrible guess. I'm going to guess that the x-intercept is this value right here, whatever x is there. I'm going to call it x naught or x sub 0, our initial guess as to what the x-intercept is. And I think pretty obviously we can see that this guess is terrible. This is clearly not the actual x-intercept of this function. So what we're going to do is we're going to go up to our function up here, and we're going to say our function does have a point at x naught. Right? Some point up here. That would be the point x naught. And this is the function f of x. Right? And we'll do that. We'll call this function f of x. So function has a point there. The function also has a derivative there. The function has a tangent line there. And we could sketch the tangent line at that point. So I'm going to do that. I'm going to try to just kind of ballpark it. I know that's not perfect, but let's say that's our tangent line at x naught, f of x naught, to our function f of x. And one, we can see that this function that we've drawn, this equation that we've drawn, this line here, has an x-intercept. And I'm going to mark that as x1. And we're going to note that that x-intercept is a better approximation for the actual x-intercept of our function than our original guess was. And it'd be nice if we could, knowing what our initial guess x naught was, we should then hopefully be able to find the value of x1. In order to do that, though, we would need to know the equation of the line that we drew that gave us x1. So let's see if we can write the equation of that line. Well, we have a point, x naught, f of x naught, and we would then need to have a slope. Well, the slope of that line would have to be the derivative of that, evaluated at x naught. So we could just use a tangent line equation there. Using point slope form, y minus f of x naught should equal m f prime of x naught times x minus x naught. And we should be able to use that equation to figure out the value of x1, because x sub 1 is just a point on that line that has an x coordinate of x sub 1 and a y coordinate of 0. So that means I'm going to replace the y in my equation here, this y right here, with 0. And get 0 minus f of x naught equals f prime of x naught times my x value here. That x value I'm talking about is x1 minus x naught. And, well, we want to know the value of x1, so we would just need to then go in and solve that for x1. The first thing to do would be to divide by f prime of x naught, so we have negative f of x naught over f prime of x naught is equal to, now it would just be x1, that value we're looking for, minus naught. And adding an x naught over to the other side of that ought to just give us x1 is now equal to x naught. And then this is a negative f of x naught over f prime of x naught. So we'll call it minus f of x naught over f prime of x naught. So a little bit of algebra there, but not too terrible. say that this x-intercept that we found for our line, x1, should be equal to our initial guess minus the value of our function f of x naught divided by the derivative of our original function f prime evaluated at x naught. Well, I'm going to go ahead and say that this value we just found of x1, while it's a better approximation, it's not good enough either. So I'm going to go up to my function and say, oh, my function has a point x1, f of x1. And my function exists there. There's the point. It also has a tangent line there. I'm going to sketch that tangent line there, x1, f of x1. And note that, oh, well, that tangent line crosses through the x-axis at some point. We'll call that point x2. And that value of x2 is clearly a better approximation for the value of our actual x-intercept over there, a little bit to the left of it. And well, theoretically, we should be able to find the value of x2 now that we know the value of x1. We would just go through that exact same process that we had previously done to find x1, except instead of using the point x naught f of x naught, we'd use the point x1 f of x1. And instead of using f prime of x naught, we'd use f prime of x1. So it would be, the equation of that line would be y minus f of x1 equals f prime of x1 times x minus x1. And well, just like we did, we could then say that x2 has the coordinates x2 comma 0. We could replace the y value with 0 and the x value with x2 and go ahead and solve. And I think it's probably pretty plain to see that if we did that, we'd end up with the exact same thing that we got over here, except instead of x1, it'd be x2, and all of the x naughts would be replaced with x1. So I think we could say that x2 ought to be equal to x1 minus f of x1 over f prime of x1. And that'd be our value at x2. And as we said, we've got a nice value there at x2, but it's still not close enough. We'll just go up here and say, there's a point x2 f of x2, and our function has a tangent line there. And that tangent line has a x-intercept, which we could call x3. And I think we could probably go in and say the value of x3 is probably equal to, in fact, it definitely is equal to x2 minus f of x2 over f prime of x2, just not squared, x2, just using that same process that we have used over and over and over again. And x3 is a pretty good approximation. It's getting closer. And I think now it's pretty obvious to see that if we wanted to, we could just repeat this process as many times as we felt like repeating this process until we got as close to the true value of the x-intercept for f of x that we might want to find. I could go up here, find this point, find a tangent line there, and see that, oh, we're getting just a little bit closer. We're now very close when we get to x4, and x5 would be just a little bit closer, and x6 would be just a little bit closer. And we're never going to get exactly to that x-intercept, but we can get to within any number of decimal accuracy to that actual x-intercept that we want, just by repeating this process, by repeatedly finding the equations of the tangent lines and finding their x-intercepts. This method is called Newton's method for finding roots of an equation or x-intercepts of an equation. Newton's method. And so we're going to want to use this formula that we've now seen a few times, right? That the next x-intercept guess is equal to the previous x-intercept guess minus the function at that x-intercept divided by the derivative of the function at that x-intercept. So in generic terms, that's going to look like this. X sub n plus 1 equals x sub n minus f of x sub n over f prime of x sub n. And this is Newton's method for approximating roots. It uses linearization to do so. And we're going to always remember when we use this formula to show a reason why you picked your first guess of what the root might be. Don't just pick a million and hope it's going to eventually work out. But find a reasonable guess and use that reasonable guess. Explain why you use it. So let's take a look at this function. X cubed plus 3x plus 1 equals 0. And we're going to go ahead and use Newton's method to approximate the root of this equation. Solve this equation. So the first thing that we're going to need is we will need our Newton's method formula, which means that we need to find the derivative of it. So we'll say f of x is equal to x cubed plus 3x plus 1, then f prime of x must equal 3x squared plus 3. And so now when we go in to write our formula, x sub n plus 1 is equal to x sub n minus f of x sub n. So that'll be x sub n cubed plus 3x sub n plus 1 over f prime of x sub n, which will be 3x sub n squared plus 3. And now we need the first guess for what our root might be. Well, I think we can see that f of 0 is equal to 1. And if we then tried to figure out what f of negative 1 was, that'd be negative 1 cubed, that'd be negative 1. And then plus 3 times negative 1, that'd be minus 3, plus 1. Well, that value is negative 3. And we can see that between negative 1 and 0, the function crosses through the x-axis by the intermediate value there. We could say that f of x is continuous on negative 1 to 0, and f of negative 1 is less than 0, f of 0 is greater than 0. There's a sign change, therefore there must be a root on the interval negative 1 to 0 by the intermediate value theorem. Right? The intermediate value theorem. And so using that, we should then be able to say a good guess, a good first guess, let's say x naught should be negative about 0.5, just something right there between negative 1 and 0. And so what we're going to do then is we're going to use our calculator to approximate this. So we're going to go back into our graphing calculator here. And there's a little series of steps that we're going to need to take here. And the first is to just type in our first guess of negative 0.5, and then just hit enter. And what's that doing? Well, that's storing negative 0.5 as our previous answer. And then we're going to go in and we're going to type in our entire formula that we just wrote, the x sub n plus 1 equals x sub n minus f of x sub n over f prime of x sub n, with our function in it. But instead of typing x sub n, because there's no x sub n key on here, and we're just going to use the answer button. And it's going to utilize the previous answer that we've inputted into our calculator. So that means that it's going to use negative 0.5 as the value every time we say answer. So every x sub n is going to be an answer. So we're going to type in, start with x sub n or answer minus. And then our formula is this nice fraction, x sub n cubed plus 3x sub n plus 1 over 3x sub n squared plus 3. So you can either use this alpha and turn it into this fraction if you have that possibility on your graphing calculator. But if you don't have that possibility on your graphing calculator, you're going to want to open up a parenthesis to start the entire fraction. And then you're going to open up a second parenthesis to start the numerator of your fraction. And we've got x sub n cubed. So we'll start with answer, the second and the negative sign, cubed, answer cubed, plus 3 times x sub n, so plus 3 answer, and then plus 1. And that's the end of our numerator. So we'll close the first parenthesis. We'll say divided by. And then we'll open a new parenthesis for our denominator, which is 3 times x sub n, or answer, squared, plus 3. We'll close the parenthesis for the denominator, and we'll close the parenthesis for the entire fraction. And so what we'll do is we'll hit enter, and it's going to give us the evaluation of that at negative 0.5. And the cool thing about the TI calculators here is if I just hit enter again, it's going to reutilize that exact same formula, except this time, instead of using negative 0.5 as the answer, it's going to use this answer I just got of negative 0.333 repeating, which is exactly what I want it to do. I want to then evaluate it at that x value. And so if I hit enter, we'll see that it gives us now negative 0.32222 repeating. And if I hit enter again, it's going to give us another value there. And if I hit enter again, it's going to use that. And we can see it's getting closer and closer and closer to being exactly the same each time, right? That we've got 0.322185355, and then 0.32218535546. If we hit it one more time, it's going to give us the exact same complete decimal there. Looks like we've got 10 decimals there after the decimal point. And they're all exactly the same, which means this is now accurate to 10 decimals for what that x-intercept is for that function. And so we are now finished. That's going to be our answer, negative 0.32218535546. But what I will ask you to do, which probably won't like too much, is to go in and list out the values that you got. So we started with x sub 0, or x naught is negative 0.5. We then had x1 came out to be negative 0.3 repeating. I'm just going to represent on 3. Our next value, x sub 2, was negative 0.32, and then just the 2 was repeating. And then our x sub 3 was equal to negative 0.322185355. And x sub 4 was equal to negative 0.32218535546. And then the next one, x sub 5, was the same. I'm just going to say that's the same. It's the same as x sub 4, which means that this is the best approximation our calculator can give us for the solution of the x-intercept of x cubed plus 3x plus 1. And this is a more accurate approximation than what you'd get if you were using it within the graph function, just because this is giving us 10 decimals, and within the graphing function, it only usually gives us 6 decimals. And so that's the process we're going to use to find the solutions to equations or approximate roots using Newton's method. So let's take a look at another one. We want to approximate the 5th root of 7. Well, in order to do that, we have to think a little bit about the function that we might want to use here. We want the x value that we're getting to be the 5th root of 7. So we have to develop an equation that has the 5th root of 7 as its root. Well, that should be pretty easy to do. We'll just raise both of these to the 5th power and say x to the 5th equals 7, or say x to the 5th minus 7 is equal to 0. And so now, if we can find an x-intercept using Newton's method of x to the 5th minus 7, that should be the value of the 5th root of 7. So we'll say that f of x is equal to x to the 5th minus 7, giving us f prime of x is equal to 5x to the 4th. And we'll note that if I plug in 1 to this, f of 1 is 1 minus 7, that's negative 6. And f of 2, well, 2 to the 5th is 32. So 32 minus 7 is 25. We'll note that f of 1 is a negative value and f of 2 is a positive value. And since f of x is continuous, it being a polynomial, on the interval 1 to 2, the IVT guarantees a solution on the open interval between 1 and 2. So we know that we'll probably want to start off with something between 1 and 2 as our initial guess. So I'm going to say, let's write out our formula. X sub n plus 1 is going to be x sub n minus f of x sub n, which in this case is just going to be x sub n to the 5th minus 7 over 5 times x sub n to the 4th power. So this will be what we're using to approximate our root. And let's say we'll start with x naught is equal to something between 1 and 2. 1.5 seems right, like a reasonable value for us to use. So we will now go into our calculator, clear out all of this. Our starting guess is 1.5, so step 1 will be just to put in 1.5 and hit enter. And from there, we'll now put in our formula. And instead of every x sub n, we'll use the answer key. So second answer minus 2 parentheses, 1 for the fraction as a whole and 1 for the numerator. And it's x sub n to the 5th, so that'll be answer to the 5th power minus 7. Close that first parenthesis for the numerator, and then divided by, and then second parenthesis here for our denominator. 5 answer to the 4th power. And we'll close the denominator parenthesis and close the fraction parenthesis as a whole. And we will hit enter, giving us an approximation of that, or give us a value of that using 1.5. We will hit enter again and see that it's not quite exactly the same yet. So we'll hit enter again, getting closer to being the same, but still not quite there. But here, it looks like on the 4th time we've hit enter, those two values came out to be identical. And so we can stop right there and say that that's as accurate as our calculator is going to give us the value for the 5th root of 7. We'll go back in. We'll write out those values. That x naught was 1.5. X sub 1 was 1.4765431. X sub 2 was 1.47573964. X sub 3 was 1.47573162. And x sub 4 was the same as x sub 3. And we can call this the best approximation of the 5th root of 7 that we'll be able to get. So we'll just do one more here. We're going to use the function f of x is equal to x cubed minus x minus 2, giving us f prime of x is equal to 3x squared minus 1, which means that using our Newton's method formula, x sub n plus 1 needs to equal x sub n minus x sub n cubed minus x sub n minus 2, all over 3x sub n squared minus 1. And you want to make sure you write that formula each time. And we'll note, once again, that f of x is continuous. And and it's because it's a polynomial. Check that out. And we need to find a good interval that we're going to look at here. Continuous for all real numbers. And so if we think about what f of, f of 0 looks like, it's -2, but f of 1 also looks like it's -2. Let's write that down. F of 1 is equal to -2. But f of 2, well, that's 8 minus 2 minus 2. F of 2 is equal to 4. So it looks like our sign change occurs between 1 and 2. So our function is continuous for all real numbers, particularly on 1 to 2. And that tells us, since we have a sign change here, f of 1 is negative and f of 2 is positive, we must have a sign change, which means we must have an x-intercept by the IVT. It guarantees an x-intercept on the open interval 1 to 2. So seems like a good first guess, once again here, would just be x naught is equal to something between 1 and 2. We'll go with 1.5. And once more, we'll go back into our calculator, clear up all this other work that we were doing a bit ago, and we will start with our first guess of 1.5. Hit enter to save that as our previous answer. And we will have answer minus, again, 2 parentheses, one for the fraction, one for the numerator. We had x sub n cubed, so that'd be answer cubed, minus x sub n, that'd just be answer, minus 2. We'll close that parenthesis, and we'll divide that by what we had in the denominator, which was 3x sub n squared. So we'll say 3 answer squared, and then minus 1. Close the parenthesis for the denominator, close the parenthesis for the whole fraction, and we'll hit enter. And well, that didn't give us a value even between 1 and 2 to start with. But if we hit enter again, it looks like it did this time. And we've jumped kind of far down there and jumped up even further. We can see, I've screwed this up. I didn't get my equation in properly. I was supposed to have answer cubed minus answer, but I multiplied them together. So if you're jumping back and forth like this, you can see that you made a mistake like I did. I'm going to have to go back in and restart all of this. We're going to go with 1.5 again, and then we'll hit enter. This time I'll try and do this correctly. Answer minus answer to the 3rd power minus answer. This will work out a lot nicer for us if we actually type the equation in correctly. So minus answer minus 2 divided by 3 answer squared minus 1, and then close our 2 parentheses. And that looks a lot nicer. We're actually getting a value that's close to what we were looking for. If we hit enter a couple more times here, looks like right there on our 4th time, we again get a value that is repeated. So we'll use that. We'll go in here and say x sub 1 was 1.52173913. X sub 2 was 1.521379,806. X sub 3 was 1.521379707, and x sub 4 came out to be the same as x sub 3, giving us this as our best approximation for the x-intercept of that function on that interval. And so just a couple things to remind you of. One, make sure you write out this equation for Newton's method. Make sure you list out the values that you get, and make sure you give a reason why you used your starting value as your starting value. And make sure you type the equation for this in correctly into your graphing calculator, because if you don't, you'll get something screwed up like I almost did for this one here. So those values should kind of approximate down to like a very, very accurate approximation quite quickly. And if it's not doing that, it's quite likely that you put in your equation incorrect. And that's it for today. We're done talking about Newton's method, and we'll look at some new stuff with tangent and secant lines next time.